On April 18, 1955, global newspapers reported the death of the renowned scientist. They featured a picture of Albert Einstein's workspace, displaying an open notebook where he recorded notes and worked on the theory that would define his life's work, the unified field theory, also known as the theory of everything. This theory aims to amalgamate all the natural forces, gravity, electromagnetism, and strong and weak nuclear interactions, into a single equation. Einstein's pursuit of this equation stemmed from his conviction that comprehending the fundamental laws governing the universe would enable humanity, as he expressed it, to read God's mind. 6 years earlier, 2 weeks after his 70th birthday, which he described as a sad event, Einstein, in a letter to Maurice Solovine, dated March 18, 1949, admits, "You think that I look at my life's work with a sense of complete satisfaction. Up close, however, everything looks different. There is not a single concept about which I am sure that it will remain immutable. I'm not even sure I'm on the right path at all. My contemporaries see me as a heretic and a reactionary who, so to speak, has outlived himself. All this is, of course, a matter of fashion and is explained by their underthinking. But a sense of dissatisfaction rises in me from within. To overcome the mathematical difficulties in creating a unified field theory, Einstein could not succeed for decades. At the same time, of course, he did not consider his work useless or meaningless. On the contrary, in a letter dated December 14, 1946, Michel Besso, with whom he shared the most intimate, the scientist calls it fruitful and believes in the future. Hope permeates his letter to Michel of April 15, 1950, although Einstein is aware of the unthinkable complexity of the task. Hence, it appears that the possibility of comparison with something known from experience is to be expected only when the solution strings of a system of equations are found in which the images known from experience and their variable influences are reflected. But, since this is monstrously difficult, one can understand the skeptical position of modern physicists. So far, they have every right to consider my path unfruitful, but it won't last long. Gradually, they will see that, with the help of quasi-empirical method, the essence of things cannot be understood. How did the author of the theory of relativity and the iconic formula which elucidated the fundamental mass-energy relationship almost become a dissident by the end of his life in the eyes of modern physicists? In the 1920s, physicists admired and held high hopes for Einstein's pursuit of a unified field theory. However, by the 1930s, amidst the remarkable advancements of quantum mechanics and quantum field theory, Einstein's influence waned considerably. His attempts to derive specific equations governing the motion of elementary particles from his overarching framework proved unsuccessful. Meanwhile, quantum physics demonstrated astonishing productivity. The year 1932 marked a significant period of discovery. Just 5 years after the establishment of the Copenhagen interpretation of quantum mechanics, 2 new elementary particles were discovered: the neutral neutron, found alongside the proton in atomic nuclei, and the positively charged positron, identified as the antiparticle of the electron, as predicted by Paul Dirac. Intriguing historical paradox. The credit for the discovery of antiparticles should have arguably belonged to Albert Einstein, but he overlooked this opportunity due to his fervent focus on the quest for a unified field theory. 3 years before Dirac, in the fall of 1925, Einstein published in the Dutch journal Physica a short article entitled "The Electron and the General Theory of Relativity." It begins with an unusual phrase for scientific articles. The following remarks are so simple that I do not hope to say anything new in them. From the position of today's understanding of physics, this phrase indicates that the author has not fully realized the genius of what he has done. After all, we are talking about nothing less than the discovery of antimatter. This instance vividly illustrates Einstein's unwavering dedication and concentration on the theory of everything. Some of Einstein's scientific peers regarded his endeavors with sympathy, while others even made jests at his expense. Nevertheless, the immense challenge did not deter Einstein. Until his final days, he grappled with mathematical conundrums tirelessly, much like Don Quixote battling windmills. Not in vain, and Einstein himself recalls the hero of the novel Cervantes in that letter of April 15, 1950, in one of his last messages to Michel Besso. It is true that under such circumstances one finds oneself in the position of Don Quixote, since there is no certainty that there will ever be an opportunity to find out whether your theory is true or not. But the longer the struggle for a unified field theory lasted, the more doubts came to mind. In a later letter to a friend, they're expressed most vividly. The whole 50 years of conscious search have not brought me any closer to the answer to the question, what are the quanta of light? Today, any passerby thinks that it is known to him, but he is mistaken. I am now sure of the possibility of a natural generalization of the gravitational equations, but I cannot find out whether there is anything physically true behind it. Erwin Schrödinger, Werner Heisenberg, Niels Bohr, Paul Dirac, Max Planck, Richard Feynman, Julian Schwinger, Abdus Salam, Stephen Weinberg, Sheldon Glashow, Stephen Hawking, Roger Penrose, John Wheeler, David Hilbert, Hermann Weyl, Oscar Klein, Edward Witten, Brian Greene, Juan Maldacena, Michael Green, John Schwartz, Gerard Hooft, Carlo Rovelli, Lee Smolin, Kip Thorne. The roster of scientists who have delved into the theory of everything could extend indefinitely. Yet did any of them manage to unveil the elusive God equation? Presently, numerous prominent physicists assert that we are edging closer to a resolution. String theory emerges as a primary contender for a theory of everything. It proposes that the universe comprises not point particles but minuscule, vibrating strings, with each note corresponding to an elementary particle. According to this theory, when observed through a powerful microscope, elementary particles like electrons, quarks, and neutrinos appear as vibrations of minuscule threads reminiscent of stretched rubber bands. By manipulating these bands in various ways, we generate all the recognized elementary particles in the universe. Consequently, all laws of physics can be simplified to the harmonious interactions of these strings. Chemistry is melodies that can be played on strings. The universe is a symphony, and God's thoughts, about which Einstein wrote so eloquently, are cosmic music resonating in space-time. Nobel Prize-winning physicist David Gross wrote, "String theory is a piece of 21st century physics that accidentally fell into the 20th century." And here are the words of Kip Thorne. String theory is an amazing theoretical development that attempts to bring all forces of nature together into a single coherent picture. It is a bold and beautiful idea and has captured the imagination of physicists around the world. The pursuit of a comprehensive theory such as string theory holds significance beyond academia. Each breakthrough in understanding the laws of physics reshapes civilization and impacts the destiny of humanity. For instance, Newton's laws of motion and gravity paved the way for the age of machinery and the Industrial Revolution. Michael Faraday and James Clerk Maxwell's work on electricity and magnetism facilitated city lighting, electric motors, generators, television, and radio. Einstein's equation elucidated the energy source of stars and enabled harnessing atomic energy. Pioneers of quantum mechanics like Erwin Schrödinger and Werner Heisenberg initiated today's high-tech revolution, leading to quantum supercomputers, lasers, the internet, and ubiquitous gadgets. The marvels of modern technology stem from scientists' inquiries into the fundamental interactions of our world. Currently, science appears on the brink of formulating a theory that unifies the four fundamental forces of nature. A comprehensive theory of everything raises several profound questions. What occurred before the Big Bang? Why did the Big Bang initiate? What constitutes dark matter and dark energy? What resides within a black hole? Is time travel feasible? Do wormholes exist, leading to alternate universes? How many universes exist, and what are their characteristics? Are there additional dimensions? How do we interpret phenomena like the double-slit experiment and quantum superposition of electrons? This video delves into the pursuit of a definitive theory, exploring pivotal moments in the history of physics. It revisits past breakthroughs, from Newton's paradigm shift to advancements in electromagnetism, the formulation of relativity and quantum mechanics, to contemporary string theory and emerging concepts. Physicists and mathematicians aim to formulate a singular equation encompassing the spectrum from subatomic particles to cosmic structures, unraveling the fabric of reality. Simpler and more practical expressions of love and interest in science can be found in ways such as reading books by Michio Kaku, one of today's most famous theoretical physicists, co-founder of string field theory. He wrote the book, The God Equation. the quest for a theory of everything, which served as the inspiration for this video, offering an enjoyable and structured approach to expanding knowledge. And next, we will be uncovering the main topic of the video, the theory of everything. The ancient Greeks were among the first to seek order in a seemingly chaotic world. Philosophers such as Aristotle proposed to explain everything through combinations of four primary elements: earth, air, fire, and water. However, these elements could not explain the observed complexities. Greek thought offered two different explanations for this complexity. The first explanation came from the philosopher Democritus, who suggested that everything was made up of tiny and invisible, indecipherable particles called atoms, which in Greek means indivisible. Critics contested the existence of atoms, citing their minuscule size as an obstacle to direct observation. Nonetheless, Democritus presented persuasive indirect evidence, such as the gradual erosion of a golden ring, implying the presence of atoms despite their invisibility. Even today, much of our scientific comprehension relies on circumstantial evidence. Details about the sun's composition, the intricate structure of DNA, the universe's age, and more are inferred through indirect measurements, despite never directly observing these phenomena. This differentiation between direct and indirect evidence holds significance in discussions concerning the validation of unified field theory. A contrasting approach to comprehending the world emerged from the mathematician Pythagoras. Inspired, Pythagoras applied a mathematical framework to earthly phenomena, particularly music. Legend has it that he discerned a correlation between the sound produced by a lyre's strings and the vibrations elicited by striking a metal rod with a hammer. Pythagoras' realization that both produced musical frequencies within a certain range hinted at the harmonious relationship between aesthetics and the mathematics of vibrations. This discovery suggested that the pleasing qualities of music could be rooted in mathematical principles, implying that diverse objects in the world might adhere to the same mathematical laws. Essentially, the variety of objects surrounding us must conform to mathematical principles. In the 17th century, a wave of scientists dared to challenge prevailing beliefs and delve into the nature of the universe. Johannes Kepler stands out as one of the pioneers who employed mathematics to comprehend planetary motion. Despite serving as an imperial advisor to Emperor Rudolf II, he faced persecution for incorporating religious elements into his work. Meanwhile, former monk Giordano Bruno faced a grimmer fate. In 1600, he was convicted of heresy and executed for suggesting the possibility of life on planets orbiting other stars. Galileo Galilei, often hailed as the father of experimental science, narrowly evaded a similar fate. Confronted with the threat of death, Galileo renounced his theories, yet his legacy endured through the invention of the telescope, a device that transformed the scientific world. Through the telescope, it became evident that the moon's surface was adorned with craters. Venus exhibited phases corresponding to its orbit around the sun, and Jupiter boasted its own moons, all notions previously deemed heretical. Regrettably, Galileo endured house arrest and was barred from receiving visitors. Over time, Galileo's eyesight deteriorated, likely due to observing the sun through his telescope. He passed away a broken man. However, in the year of his demise, a child was born in England who would carry forward the work of Galileo and Kepler, ultimately formulating a unified theory of celestial mechanics. Isaac Newton, arguably the most influential scientist in human history, defied a world preoccupied with magic and witchcraft by daring to formulate universal laws of celestial mechanics. He utilized newly developed mathematical methods, integral and differential calculus, to investigate natural phenomena. As physicist Steven Weinberg stated, "It is with Isaac Newton that the modern dream of a definitive theory truly begins." At one point, Newton's theory was seen as a theory of everything, capable of describing any motion. It all began when Newton was 23 years old. Cambridge University was closed due to the plague. One day in 1666, walking on his estate, he saw an apple fall, and he asked himself a question that would change the course of human history. When observing the falling apple, Newton pondered whether the same force causing its descent also influenced the motion of the moon. He sketched a pivotal drawing in his notebook, illustrating the scenario. If a cannon were fired from a mountaintop, the cannonball would travel a certain distance before succumbing to gravity and falling to the ground. However, if the cannonball's speed were increased, it would travel farther and, with sufficient velocity, could potentially circumnavigate the world. Newton concluded that the same law of nature that governs the motion of apples and cannonballs, namely gravity, is responsible for the motion of the moon around the Earth. To elucidate this principle, Newton introduced the concept of forces. He posited that objects move due to being pulled or pushed by forces that are universal, quantifiable, and subject to mathematical description. Thus, Newton introduced the foundational notion of unification in physics. In 1682, a monumental event unfolded, altering the course of history. A brilliant comet graced the sky, captivating people from all walks of life, from royalty to commoners. Questions abounded. Where did it originate? Where was it bound? What did its appearance signify? Among those intrigued was Edmund Halley, an astronomer of note, who journeyed to Cambridge to meet Isaac Newton. By then, Newton had garnered renown for his theory of light, demonstrated by his experiment of passing a sunbeam through a prism, revealing its division into the colors of the rainbow. Newton also pioneered a novel type of telescope employing mirrors rather than lenses. Inquiring about the widely discussed comet, Halley was astounded to discover that Newton could substantiate that comets follow elliptical orbits around the sun, and could even forecast their trajectories using his theory of gravity. Furthermore, Newton had observed comets through a telescope of his own design, verifying his predictions with their actual motions. Halley recognized the profound significance of this scientific breakthrough and generously offered to finance the printing costs of Newton's seminal work, The Mathematical Principles of Natural Philosophy, destined to become one of the most pivotal scientific publications. True to Newton's calculations, Halley's comet graced the European night sky in 1758, solidifying the enduring legacies of both Newton and Halley. Newton's theory of motion and gravity stands as one of humanity's most remarkable intellectual accomplishments due to its unifying principle encompassing all known laws of motion. NASA engineers continue to rely on Newton's laws to navigate space probes through our solar system. Over the centuries, numerous validations of Newton's laws have emerged, profoundly shaping both scientific understanding and societal progress. In the 19th century, astronomers made a puzzling observation. The orbit of Uranus displayed significant deviations from Newton's predicted path, suggesting either an exception to his laws or the gravitational influence of an undiscovered planet. Confident in Newton's laws, physicists like Urbain Le Verrier calculated the hypothetical position of this unseen planet. In 1846, astronomers located the planet precisely where predicted, deviating by only 1 degree, and named it Neptune. Newton's laws unlocked the secrets of planets and comets, laying the groundwork for mechanics. Today, they underpin the construction of bridges, skyscrapers, engines, jet airplanes, trains, rockets, and space probes. These are not just boring equations. They form the backbone of our comprehension of reality, driving a profound consequence, reshaping modern civilization and fostering the wealth and prosperity we witness today. By bridging celestial and terrestrial physics, Newton's laws ignited the first significant technological revolution. It would be another 2 centuries before the next major breakthrough, stemming from the exploration of electricity and magnetism, would emerge. Even in ancient times, people recognized the potential of harnessing magnetism. The Chinese invention of the compass expedited geographical exploration. However, electricity was viewed with fear, often associated with divine wrath, as exemplified by the belief that lightning was a manifestation of God's anger. Michael Faraday pioneered a new realm of understanding. He demonstrated that moving a magnet within a wire loop generates electricity within the wire, revealing the interconnectedness of electric and magnetic fields. Faraday's realization that these phenomena were interconnected marked the dawn of the electrical age, facilitating the construction of hydroelectric power plants capable of illuminating entire cities. Additionally, Faraday introduced the concept of the field, a cornerstone of physics. A field is made up of lines of force that fill space. Magnetic lines surround every magnet, and the Earth's magnetic field emanates from the North Pole to the South Pole. Even Newton's theory of universal gravitation can be interpreted from a field perspective. The Earth revolves around the Sun because it is within its gravitational field. Faraday's discovery helped elucidate the origin of the Earth's magnetic field. As the Earth rotates, its internal electrical charges also move. This constant movement within the Earth is what creates its magnetic field. Currently, all known natural interactions of the universe are described precisely in the language of fields, first introduced by Faraday. However, the study of fields required a new field of mathematics, namely vector calculus, which was used by James Clerk Maxwell. Maxwell was a master mathematician who made a remarkable breakthrough in physics. He realized that the behavior of electricity and magnetism, described by Faraday and others, could be generalized and expressed in precise mathematical language. But there was one oddity. One law stated that a moving magnetic field produces an electric field. The second law stated the opposite, that an electric field can produce a magnetic field. How could that be? Maxwell had a brilliant idea. What if an alternating electric field creates a magnetic field, which in turn generates another electric field, which then generates another magnetic field, and so on? He guessed that the end result should be a traveling wave in which electric and magnetic fields constantly alternate. Using vector calculus techniques, Maxwell calculated the speed of this traveling wave and obtained a value of 310,740 kilometers per second. The result astounded him. Within the experiment's error, the resulting speed was remarkably close to the speed of light. He then took another bold step and claimed that this was light itself. Light is an electromagnetic wave. Today, Maxwell's equations form the basis of television, lasers, electric motors, generators, and much more. Not only have they given us the ability to communicate almost instantaneously through radio, cell phones, and fiber optic cables, but they also opened up the entire electromagnetic spectrum, in which visible light and radio waves are but two bands. In 1660, Newton demonstrated that white light could be divided into all the colors of the rainbow by passing it through a prism. In 1800, William Herschel asked himself a simple question: what lies beyond the edges of the rainbow? The colors in which change from red to violet. He took the prism he used to produce rainbows in his laboratory and placed a thermometer behind the red, where no color could be seen at all. Suddenly, the temperature in this seemingly empty space began to rise. This meant that there was another color besides red, invisible to the human eye, but still containing energy. It was called infrared light. Now we understand that there is a whole spectrum of electromagnetic radiation, most of which is invisible, because each region of it is characterized by a specific wavelength. This means that all of the reality we see around us is just a tiny slice of the electromagnetic spectrum. That is, the tiniest element of a much larger universe of electromagnetic hues. Some animals see much more than we do. Bees, for example, are able to perceive ultraviolet radiation, invisible to us, but important to bees because it helps them find the sun and navigate by it, even on a cloudy day. And since flowers have evolved their gorgeous colors to attract the insects needed for pollination, such as bees, this means they often look even more attractive when viewed in the ultraviolet range. And the peacock mantis crayfish has 12 types of photoreceptors that perceive a range of wavelengths from 300 to 720 nanometers. That means it sees in the optical infrared and ultraviolet ranges of the spectrum at once. It's a predator. Combining Newton's and Maxwell's equations gave us a very convincing theory of everything, at least everything, that was known at that era. At the turn of the 19th and 20th centuries, many scientists declared the end of science. It was a tumultuous period when it was believed that everything that could be discovered had already been discovered. At the time, physicists did not know that the two pillars of science, Newton's equation and Maxwell's equation, actually contradicted each other, and one of them was destined to fall. And the clue was in the hands of a 16-year-old. This man was born in 1879, the year Maxwell died. As a teenager, Einstein asked himself a question that was destined to change the course of the 20th century. He asked himself if it was possible to outrun a ray of light. Many years later, he would write that in this simple question was the key to his theory of relativity. Over the next decade, he searched hard for the answer. Unfortunately, he was perceived by many as a failure, despite his exceptional academic record. His professors did not approve of his reckless approach to life. Since he was already familiar with most of the material, he often skipped class, leading to unflattering evaluations from his professors. All of his job applications were met with rejection. At one point, wanting to support his common-law wife and child, he even considered selling insurance policies. Imagine opening the door and seeing Einstein trying to sell you insurance. Unable to find work, he felt like an outcast in his own family. In one of his letters, he wrote gloomily, "I'm just a burden to my family. I'd rather not be in the world at all." Eventually, he managed to get a job as a third-class clerk in the patent office in Bern. In the silence of the patent office, Einstein was able to return to the question that had tormented him since childhood. It was there that he was destined to start a revolution that turned physics and the world upside down. Einstein wondered what would happen to Maxwell's equations if an object moved at the speed of light. Interestingly, no one had ever asked this question before. Using Maxwell's theory, Einstein calculated the speed of a light beam relative to a moving object, such as a train. He expected that the speed of this light beam, observed by a stationary observer outside, would be the sum of the ordinary speed of light and the speed of the train, because, according to Newtonian mechanics, the velocities must add up. To Einstein's surprise, he found that the beam of light continued to travel away at the same speed. However, this seemed impossible. According to Newton, if you move fast enough, you can catch up with anything. Common sense would suggest the same thing. However, Maxwell's equation stated that it was impossible to catch up with light. This realization was a revelation to Einstein. Only one of them could be right, either Newton or Maxwell. But why couldn't light catch up? Einstein's insight was that because the speed of light is measured with clocks and rulers and is constant, no matter how fast you move, space and time must warp to ensure this constancy. This means that if you are in a fast-moving spaceship, the clocks inside the ship will go slower than on the ground. That is, the faster you move, the slower time flows. This phenomenon is described in Einstein's special theory of relativity. Consequently, the answer to the question, "What time is it now?" will depend on your speed. Here's an example. Imagine that you are observing a spaceship in space from the ground using a telescope, and it is traveling at close to the speed of light. In such a case, the objects inside the ship will be compressed and will move very slowly. At the same time, for the astronauts themselves inside the ship, everything will look fine. They will not notice these effects. Later, Einstein said, "I owe Maxwell more than anyone else." Today, such an experiment is not difficult to do. If you put an atomic clock in an airplane and compare it to a clock on the ground, you will see that it goes slower by a tiny fraction of 1/1,000,000th. But if space and time can change, so must everything that can be measured, including matter and energy. The faster you move, the heavier you become. The source of this extra mass is the energy of motion. For example, you weigh 70 pounds. This means that if you develop a speed of 90% of the speed of light, you will weigh 160 kilograms. If you're 99%, you'll weigh about 500 kilograms. And if you accelerate a little bit more, less than 1%, to 99.99 of the speed of light, your mass will already be 5 tons. The exact relationship between matter and energy is described by the formula EMC squared. The same equation answers one of the oldest questions in science. Why does the sun shine? The answer is quite simple. The sun shines because, as a result of the compression of hydrogen nuclei at very high temperatures, some of their mass is converted into energy. The key to understanding the universe is unification. For the theory of relativity, this is the unification of space and time, as well as matter and energy. But how is it achieved? For poets and artists, beauty is a fleeting aesthetic characteristic that evokes strong emotion and passion. For physicists, beauty lies in symmetry. Equations are considered beautiful when they possess symmetry. That is, when a rearrangement or substitution of components leaves an equation unchanged, it is invariant with respect to that transformation. Similarly, a snowflake is beautiful because its shape remains unchanged when rotated 60 degrees. The sphere has even more symmetry, rotated around its center at any angle or in any direction, and it does not change. Body parts of some animals are arranged symmetrically around a central axis, such as radial symmetry in sea stars. Fractal symmetry is found in nature, in Romanesco broccoli, because the same pattern is repeated at different scales. That is, each smaller part of the broccoli is a miniature version of the whole. There are also more interesting types of symmetry. For example, scale symmetry in self-similar objects such as Sierpinski's triangle. It demonstrates scale symmetry, where the same shape appears at different scales, while the overall structure remains unchanged. The atomic structure of a crystal lattice exhibits inversion symmetry, where the arrangement of atoms remains unchanged when inverted through a center point. Symmetry at the most intuitive and profound level is understandable and even pleasing to us. It is part of who we are. The human body has bilateral symmetry, which means that it can be divided into two identical halves in a central plane. This plane runs vertically from the head to the feet, dividing the body into left and right sides, which are roughly mirror images of each other. Although the human body is not perfectly symmetrical, many of its features and structures, both externally and internally, exhibit symmetry. External bilateral symmetry is the eyes, ears, arms, and legs, for example. The internal human body also shows symmetry in organs such as the lungs and kidneys. Physicists find an equation beautiful when its parts and elements can be swapped without changing the result. That is, when there is symmetry between its components. It was clear to any physicist in the first half of the 20th century that Newton's theory of universal gravitation and Einstein's theory were incompatible. According to Einstein, if the sun suddenly disappeared, the Earth would feel its absence only after 8 minutes. In Newton's famous formula for gravity, the speed of light is not present at all. Therefore, gravity propagates instantaneously, violating the law of relativity, and the Earth should feel the absence of the sun immediately, instantly. Einstein spent 10 years describing the nature of light. Then he spent another 10 years working on gravity. The answer to the question, "What is gravity?" came to him at a moment when, reclining in his chair, he almost fell. He realized that at the moment of falling, he felt weightless. Einstein recalled this as the most joyous idea of his life. If you imagine yourself in an elevator that suddenly breaks and starts falling downward, you will feel as if gravity doesn't exist because you and the floor of the elevator will fall the same way. This correspondence between acceleration and gravity is called the principle of equivalence. Many people think that astronauts in space are weightless because there is no gravity. But in fact, the ISS and the astronauts in it fall to the ground the same way, which is what creates the illusion of no gravity. In other words, the acceleration in one frame of reference is identical to the gravity in the other frame of reference, which is due to the curvature of space. To make it clearer, let's look at the solar system. We on Earth experience gravity as a force, pulling us toward the sun. However, an observer from the outside would not see any force. To him, the space around the Earth is curved, and the void causes the Earth to orbit around the sun. This is very important to realize. It is not the force that pushes the planets, but the curved mass of space that makes the planets fall. Let's remember the two ways Einstein tested his theory of relativity. The first is gravitational lensing. In simple words, it describes how light rays, which have no mass, move in a straight line, but near massive objects, especially like black holes. Their trajectory changes due to deformation of the fabric of space. Einstein realized that by the time of the solar eclipse, he would be able to calculate experimentally that the moon warps space, and thus the trajectory of the rays. And he did. The second way is the anomalous shift of Mercury's perihelion. In the end, Einstein, having developed the special and general theory of relativity, decided by all means to create a third, even more grandiose one. His goal was to unify all known interactions in the universe into one single equation. In 1869, Mendeleev had a dream about systematizing all the chemical elements. Upon awakening, he created a table of the elements, demonstrating their periodic properties. This table united more than 60 known elements, but there were gaps in it, and Mendeleev was able to anticipate the characteristics of the missing elements, thanks to the table. But what made the elements group themselves in this way? What process or law of nature underpinned this order? In 1898, Marie and Pierre Curie discovered new unstable elements. One of them, radium, glowed with no apparent source of energy, violating the principle of conservation of energy. This pointed to the need for a new theory. Previously, scientists believed that chemical elements were unchanging and eternal. However, now in laboratories, scientists observed how some elements, such as radium, transformed into other elements, emitting radiation in the process. Scientists calculated the rate of decay, and it turned out that they decayed over thousands or even billions of years. Curie's discovery has shed light on a long-standing controversy. Geologists, studying the slow processes of rock formation, had assumed that the Earth had existed for billions of years. However, William Thomson, a renowned physicist, suggested that the Earth had cooled in just a few million years. So, who was right? It turned out that the geologists were closer to the truth. William Thomson didn't account for nuclear interaction. This process could have warmed the Earth's core for billions of years due to the decay of radioactive elements like uranium and thorium. This nuclear interaction has been the source of energy for earthquakes, volcanoes, and even continental drift. In 1910, Ernest Rutherford conducted an experiment by placing radium in a lead box with a small hole in it. From this hole came a thin beam of radiation, which he directed onto gold foil. It was expected that the gold atoms would absorb this radiation. But to his surprise, the radiation from the radium passed through the foil as if it were not there. It was a startling result. It meant that atoms were made up of mostly empty space. In 1900, Max Planck, a German physicist, investigated the simple question, why do hot substances emit light? Blacksmiths had known for centuries that when objects are heated, their color changes from red to yellow to blue. But when physicists tried to calculate this effect, they ran into a problem. Newton argued that atoms begin to oscillate faster when heated, and according to Maxwell, oscillating charges emit electromagnetic radiation in the form of light. At low frequencies, the combined model worked, but as the frequency increased, the energy of light tended to infinity, which is absurd. Max Planck then hypothesized that energy was actually being studied in discrete packets, which he called quanta. Then he discovered that he could accurately calculate the energy emitted by heated bodies. The hotter the object, the higher the frequency of its radiation. That's why today, for example, we know exactly the temperature of the sun, which is about 6,000 degrees Celsius. Following his research, Planck determined the magnitude of light packets of energy, known as quanta, and described them using a constant. If Planck's constant was zero, the equations of quantum theory would reduce to Newton's classical equations. In simple words, all that strange behavior of elementary particles such as quantum tunneling, superposition, quantum entanglement is easily converted into classical Newton's equations when Planck's constant is assigned a value of zero. This is why we do not notice quantum effects in everyday life. Our perception is based on Newton's macro laws, since Planck's constant has a very small value, affecting only the subatomic world. In 1905, Einstein applied quantum theory to light and showed that light is not just a wave, as predicted by Maxwell, but a photon particle, as predicted by Planck. It is made up of photons, which are quanta. Each photon creates electric and magnetic fields around it. These, like waves, obey Maxwell's equations. But if light exists in two forms as a particle, as a wave, is not the same strange duality inherent in the electron? The answer to this question was destined to shake not only the world of modern physics, but civilization itself to its foundations. Physicists, to their surprise, discovered that electrons, previously considered ordinary particles, can also exhibit the properties of waves. You've all heard of the two-slit experiment, showing the interference pattern of light. Yes, the same one that David Deutsch and other physicists interpret that we live in a multiverse. Let's remember what it's about. To demonstrate light interference, you can take two sheets of paper and arrange them in sequence. We make two slits in the first sheet and direct a stream of electrons onto it. It is best to do this, not with a flashlight, but with a laser pointer, or in general use, natural sunlight. It is expected that the second sheet will show two stripes, corresponding to the places where the electrons pass through. But in practice, we see a number of vertical stripes, characteristic of wave interference. Electrons, traveling through a double slit, exhibit wave properties, as if they were traveling through both slits at the same time. Even sending electrons one at a time, interference still occurs. This implies that one electron somehow passes through both slits at the same time. This is astounding, how an electron, a single particle, can affect itself as if it passed through two slits at once. Moreover, in other experiments, it has been found that electrons can disappear and then reappear elsewhere, which is very strange. If a constant Planck affected objects on a large scale, our world would be incomprehensibly strange, with objects disappearing or reappearing or being in two places at once. Quantum theory, though seemingly confusing and full of paradoxes, quickly showed startling results. In 1925, Erwin Schrödinger, an Austrian physicist, presented his famous equation that accurately reflects particle wave motion. It is so fundamental that the entire Mendeleev table can be explained through this equation. At the age of 22, the young and courageous physicist Paul Dirac decided to unify the concepts of space and time by creating a wave equation that corresponds to Einstein's special theory of relativity. He created a theory that had four-dimensional symmetry, which made it attractive and concise. The complex elements of the Schrödinger equation were replaced by a single four-dimensional equation. The Dirac equation also explained where the magnetic field in magnets comes from, without moving charges. It turned out that the electron has a rotational property called spin. It is the spins of electrons in metal that create the magnetic field. The Dirac equation opened the door to understanding a new form of matter called antimatter. It is identical to ordinary matter, that its charge is opposite. For example, an anti-electron, or positron, has a positive charge. It is theoretically possible to create antiatoms from positrons orbiting antiprotons and antiutrons. For example, people learned to create antihydrogen atoms back in the mid-90s. But when matter and antimatter come into contact, an explosion occurs, and a huge amount of energy is released. In the context of the universal theory, antimatter is of key importance, as each particle must have its own antiparticle. Previously, symmetry was something of a nice detail for physicists, but not critical to theory formation. Now, however, they were surprised by symmetry's ability to predict surprising new phenomena, such as antimatter and electron spins. They realized that symmetry was a fundamental characteristic of our universe. However, there were questions that remained unanswered. For example, if an electron has wave characteristics, what creates that wave? What exactly is vibrating? And how can a wave travel through two different openings at the same time? Why the hell can't my coffee be two places at the same time, but an electron can? The question that came into focus divided all the scientists of the world into two camps. In 1926, Max Born argued that the true essence of fluctuation is the probability of finding an electron in a particular place. Thus, we cannot know with certainty where exactly the electron is, but we can determine probability of its presence in a particular place. This approach was a real revelation. It implied that the future could not be accurately predicted. We could only estimate the probability of an event. But despite the successes of quantum theory, many criticized it. Einstein observed that the more effective quantum theory became, the less logical it seemed. The debate about the philosophical aspects of wave theory continues today. Richard Feynman, Nobel Prize winner, remarked, "I think it is safe to say that no one understands quantum mechanics." On one side of this controversy stood Einstein and Schrödinger. On the other were Niels Bohr and Werner Heisenberg, pioneers of the new quantum concept. The fate of this confrontation was decided at the 6th Solvay Congress in Brussels. In 1930, it was there that the main debate of the epoch took place, during which the giants of physics came face to face in a battle for the meaning of reality itself. Paul Ehrenfest described the moment after one of the debates this way: "I shall never forget how the two opponents left the university club before my eyes. Einstein was a majestic figure and walked calmly with a faint, ironic smile, and Bohr, terribly upset, shuffled along beside him. Einstein actively criticized quantum theory, trying to emphasize its inconsistency. However, Bohr confidently refuted each of his remarks. In response to Einstein's assertion that God does not play dice with the universe, Bohr replied, 'Stop telling God what to do.'" Most historians believe that Bohr, Heisenberg, and other supporters of the new quantum theory were the winners in this dispute. But Einstein was able to identify and show the weaknesses of quantum mechanics by pointing out its unstable philosophical foundations. Many of his arguments are relevant today, and at the center of many of them is one world-famous cat. Schrödinger proposed a mental experiment to demonstrate the paradoxes of quantum mechanics. Take a cat and put it in a sealed container with a piece of uranium. When an elementary particle flies out of the uranium, a Geiger counter will go off, triggering a gun to fire a bullet. The question is the cat dead or alive? Since the phenomenon of uranium decay is determined by quantum laws, the state of the cat must be viewed through the lens of quantum mechanics. According to Heisenberg, until the moment the box is opened, the cat is in two states simultaneously, both alive and dead. These two states intermingle until you look inside the box and establish the actual state of the cat. In other words, the fact of observation somehow mystically determines reality. To Einstein, this approach seemed absurd. He often asked his guests provocative questions. For example, does the moon exist just because a mouse is looking at it? Despite all the paradoxes of quantum theory, its incompatibility with the everyday view of the world, it had an undeniable advantage. Just think about it. The predictions of quantum theory are verified to 11 decimal places, making it the most accurate theory of all time. And Einstein himself recognized that quantum theory contained truth. In 1929, he even proposed Schrödinger and Heisenberg as candidates for the Nobel Prize in Physics. To this day, nearly 100 years later, scientists have not reached a consensus on Schrödinger's cat problem. Most physicists simply use quantum mechanics as a recipe book that always gives the right answer and ignore its subtle and profound philosophical implications. The old Copenhagen interpretation of Niels Bohr, where an observation causes its wave function to collapse, is rapidly losing its relevance because today, with nanotechnology, we can manipulate individual atoms and perform similar experiments. Therefore, the many worlds interpretation, in which reality is divided into two parts. In one, the cat remains alive, and in the other, the cat remains dead, is becoming increasingly popular. After success in quantum theory, physicists decided to approach a new mystery. Why does the sun shine? Since ancient times, the sun has been worshipped in different cultures, occupying a central place in them. The Greeks sang of Helios, who rode across the heavens in his shining chariot each day, illuminating the earth. The Aztecs, Egyptians, and ancient Indians also had their own versions of the sun god. Thus, the source of the luminary's energy remained a mystery for a long time. At the dawn of the 19th century, Joseph Fraunhofer, he created a spectrograph unique for its time. Light passing through a prism forms a rainbow on the screen, showing the differences in wavelengths, including dark lines. These lines appear due to quantum jumps of electrons, which either absorb or release energy. Since each chemical element has its own unique spectral lines, this allows the composition of the substance to be determined. Therefore, spectrographs are actively used, for example, in forensics, to analyze traces. By analyzing the spectral lines of sunlight, scientists have found out that the sun is mainly composed of hydrogen. Following Fraunhofer's work, astronomers, after studying the light of stars, concluded that these celestial bodies were composed of materials inherent in the Earth. This confirmed that the laws of physics apply equally throughout the universe. Erwin Schrödinger, one of the originators of quantum mechanics, asked another eternal question. What is life? Schrödinger believed that quantum mechanics could unlock the secret to the origin of life. For centuries, scientists and philosophers have hypothesized a special life force that animates matter when something invisible, like a soul, enters it. Many adhered to dualism, believing that the physical body and soul coexisted together. Schrödinger, however, was convinced that the mystery of life must be encoded in a particular molecule that obeyed the principles of quantum mechanics. Just as Einstein excluded ether from physics, so Schrödinger wanted to exclude the concepts of life force from biology. In 1944, he published a book called What is Life? In it, he described the principles according to which the code of life is transmitted from generation to generation, not because of some ephemeral soul essence, but because of a special molecule contained in cells. In those years, mankind's knowledge of molecular biology was, shall we say, guessing at the coffee grounds. However, Schrödinger's book inspired James Watson and Francis Crick to search for this key molecule. Realizing that because of its miniaturization, it could not be seen with their eyes, they used X-ray crystallography, whose wavelengths correspond to the size of molecules. X-rays passing through the organic crystals scattered to form unique patterns. These patterns help reveal the atomic structure of the crystal. Quantum mechanics is such an advanced tool that it can be used to determine the position of atoms in molecules. Similar to Lego-like constructors for children, atoms can be connected in the right order, recreating the structure of complex molecules. Watson and Crick found that DNA is a key component of the cell nucleus. Based on X-rays taken by Rosalind Franklin, they determined that DNA has the shape of a double helix. That is, the structure of DNA was discovered using quantum mechanics. This result vividly demonstrated that the process of reproduction could be shown at the molecular level. The breakthrough allowed researchers to embark on a truly ambitious project, the human genome, which aimed to obtain a detailed atomic description of DNA. As Charles Darwin predicted back in the 19th century, scientists could now create a family tree of all life on Earth. Einstein failed to create a comprehensive field theory, largely due to a lack of information about the nuclear interaction. There are two kinds of interactions, strong and weak. Given that protons are positively charged and in theory should repel each other, the nucleus of an atom should, in theory, be blown to bits. However, it is the nuclear forces that oppose this repulsion and hold the nucleus together. Without these forces, our world would simply collapse into a multitude of separate particles. Because of the strong nuclear interaction, the nuclei of many elements can remain stable for as long as the universe has existed. But there are nuclei that are unstable because of an excess of protons or neutrons. If there are too many protons, electrical forces can destroy the nucleus. If there are too many neutrons, their internal instability can cause them to decay. The weak nuclear forces can't hold a neutron forever, so it eventually decays. This produces three particles: a proton, an electron, and another particle called an antineutrino. In 1929, Ernest Lawrence created the cyclotron, which became the basis for modern particle gas pedals. The operation of the cyclotron is based on a simple principle. A magnetic field sets protons in motion along a circular path, where they receive an energy boost from the electric field at each turn. After many turns, the protons can reach energies of up to billions of electron volts. These protons are then targeted and collide with other protons. By analyzing the collisions, scientists were able to detect previously unknown particles. This process can be thought of as trying to determine the property of a piano by throwing it out of a window and analyzing the sound of the fall. Despite the clumsiness of this method, it is one of the few ways to determine the internal structure of the proton that actually works. When scientists first collided protons with a gas pedal in the 1950s, they found many unexpected particles. This shocked them, as they expected the structure of the nucleus to become simpler when analyzed in depth, but in no way more complex. These results might have led one to think that nature was acting contradictorily. Frustrated by the continuous appearance of new particles, Robert Oppenheimer suggested that the Nobel Prize in Physics should be awarded to the person who does not discover any new particles within a year. Enrico Fermi said that if he had assumed the existence of so many particles with Greek names, he would have chosen the profession of a botanist. Physicists have been overwhelmed with information about elementary particles. Because of this problem, some thought that the human mind was basically incapable of understanding the world of subatomic particles. They compared this to the way it is impossible to teach a dog math calculations. However, the situation became clearer thanks to the work of Murray Gell-Mann, according to which the proton and neutron must be composed of three smaller particles called quarks. In 1964, the omega- particle, predicted by his theory, was discovered, which earned Gell-Mann the Nobel Prize. Scientific research related to the weak nuclear interaction, which, by the way, is 1,000,000 times weaker than the strong one, continued to develop vigorously. The weak nuclear interaction is unable to hold the elements of some atomic nuclei together, causing them to decay into simpler components. This mechanism, known as radioactive decay, explains the high temperatures inside the Earth, being the cause of volcanic eruptions and earthquakes. To understand the nature of this interaction, scientists have hypothesized the existence of a new particle. For example, an unstable neutron eventually decays into a proton and an electron in a process called beta decay. To correctly describe this phenomenon, it was necessary to add another particle to the equation, called a neutrino. Neutrinos are generally called ghost particles because they are able to fly through entire planets and stars without any interaction or absorption. They are capable of traveling almost at the speed of light, and their number exceeds all the atoms in the universe. Right now, a stream of neutrinos from deep space is passing through your body, and some of it has passed through our planet before. These particles could fly freely through the solid lead that stretches from the Earth to the Sun. Wolfgang Pauli, who predicted the existence of neutrinos in 1930, once complained, "I have committed the unpardonable sin. I have introduced a particle that cannot be observed." But as elusive as this particle was, it was eventually experimentally recorded in 1956 when analyzing the powerful radiation emitted by a nuclear reactor. In an attempt to further understand the weak nuclear interaction, scientists proposed a new symmetry principle. Since the electron and neutrino are a pair of weakly interacting particles, it was proposed to combine them. This suggestion led to the creation of a new electroweak theory that combined electromagnetism and weak nuclear interactions. The electroweak theory, developed by Steven Weinberg, Sheldon Glashow, and Abdus Salam, earned them the Nobel Prize in 1979. Instead of uniting with gravity, as Einstein had envisioned, light united with the weak nuclear interaction. Thus, out of many ambiguities, a new concept known as the Standard Model of elementary particles began to take shape. The Standard Model could determine with high precision the properties of matter in the past, up to a moment, a fraction of a second after the Big Bang. However, despite the detail of the Standard Model and its ability to reflect our understanding of the subatomic world, it still had a number of gaps. First of all, it lacked gravity, which is, to put it mildly, a serious shortcoming, given that gravity affects the macrostructure of the universe. When trying to add gravity to this model, scientists are faced with unsolvable equations, making the model unsuitable for explaining some of the mysteries of the universe, such as events before the Big Bang or the contents of black holes. The Standard Model has come together by combining different theories, making it like a mosaic of different pieces. As one physicist put it, it's like putting a platypus, an anteater, and a whale together with duct tape and declaring the result to be nature's most elegant creation. There are many unspecified parameters in the Standard Model, such as the mass of quarks, the intensity of interactions, and 20 constants added artificially without a clear understanding of their origin and meaning. To understand the magnitude of the problem, let's just compare Einstein's equation and the Standard Model. Einstein's theory, for example, can be summarized in one short equation, whereas the Standard Model equation, in a highly abbreviated form, takes almost a page to write down, as it lists in detail the various quarks, electrons, neutrinos, gluons, Yang-Mills particles, and Higgs particles. All the physical laws of the universe can be derived from this single page of equations. The problem is that the two theories, Einstein's theory of relativity and the Standard Model, are based on different math, different initial assumptions, and different fields. But the ultimate goal is to combine these two sets of equations into a single finite system. Any theory claiming to be a theory of everything must contain both systems of equations, yet remain finite. So far, the only theory that can do this is string theory. In the late 19th and early 20th century, two key concepts dominated science: Newton's law of gravity and Maxwell's equation to describe light. Einstein realized that they were incompatible and was certain that one of them would turn out to be wrong. The fall of Newtonian mechanics was the starting point of the biggest discoveries of the 20th century. Today, history is repeating itself. Science is once again dominated by two dominant concepts. On the one hand, Einstein's theory of gravity, which tells us about black holes, the Big Bang, and the expansion of the universe. On the other is quantum mechanics, which studies the world of particles. However, these theories do not fit together. It is likely that the next breakthrough will bring the two together. In 1968, two scientists, Gabriele Veneziano and Michio Suzuki, discovered an interesting formula, created by a mathematician in the 18th century. This strange formula seemed to describe the scattering of two elementary particles. But how could an abstract formula from the 18th century describe the results produced by modern gas pedals? It doesn't work that way in physics. Soon other scientists, including Yoichiro Nambu, Holger Nielsen, and Leonard Susskind, realized that this formula represented the interaction of two strings. They extended this idea to a whole army of equations, representing multi-string scattering. They were then able to introduce spinning particles into string theory. String theory became something of an oil well, suddenly spewing out a fountain of new equations. But where did so many different particles come from? The theory said that each vibration of a string was like a musical note corresponding to a particular particle. Electrons, quarks, Yang-Mills particles are just different harmonies of the same vibrating string. What makes this theory unique is the inclusion of gravity. The graviton in it is one of the lower vibrations of the string. And even if Einstein had never come up with his theory of gravity, we would have found it just by looking at the lowest vibration of the same string. Here's an example. When we analyze the collision of two particles of gravitons, the result is infinite and therefore incoherent. However, in the case of the collision of two strings, the result consists of two summons that exactly compensate for each other, helping to create a finite theory of quantum gravity. As the theory developed, features began to be discovered, such as the fact that string theory can only function in 10 dimensions. This came as a real surprise to physicists, as these kinds of discoveries had not been made before. Usually theories can be adapted to any number of dimensions. It seems to us that we live in a three-dimensional space, moving left, right, up, down, and back and forth. Given time, 4 dimensions are sufficient to describe any event. For example, to make an appointment in Berlin, the address, floor, and time are sufficient. Our perception is limited to these 4 dimensions, and it is almost unrealistic to imagine additional dimensions. That is why the study of multidimensionality in string theory is done mainly with the help of mathematics. If the assumptions of string theory are true, then our universe was originally 10-dimensional. However, such a model of the universe would have been unstable, and 6 of the 10 dimensions eventually collapsed, becoming so minuscule that atoms are too large for them to interact. Symmetry in equations has long been considered a good but not necessary quality. But in quantum physics, symmetry becomes a key element. Michio Kaku writes, "Only in the last decade have physicists realized that symmetry is not just a nice property of a theory, but rather a central component of it. Requiring a theory to be symmetric can often banish the divergences and anomalies inherent in asymmetric theories. Symmetries are the sword by means of which physicists defeat dragons, let loose by quantum corrections." Dirac found that his equation for the electron indicated the spin of the electron, a spin-like property familiar to us in everyday life. It was later discovered that all elementary particles have spin, which can be integer or half-integer. Particles with integer spin, such as photons, Yang-Mills, particles, and gravitons, are called bosons and carry the fundamental interactions of the universe. On the other hand, particles with half-integer spin, including electrons, neutrinos, and quarks, are called fermions. It is fermions that make up protons and neutrons, and hence the atoms that form our matter. Jean-Luc Gervais then showed that string theory has a new type of symmetry called supersymmetry. It's now the most comprehensive symmetry ever discovered in physics. It unites all known particles. This symmetry allows you to substitute particles for each other in equations without changing the underlying structure. Each particle has its twin in this symmetry, which is called a superparticle. For example, the pair for an electron is an s-electron, and for a quark is an s-quark. Michio Kaku writes, "In string theory, something remarkable happens. When we calculate quantum corrections to string theory, we have 2 components. There are quantum corrections coming from fermions, and there are quantum corrections coming from bosons. They are miraculously equal in magnitude, but opposite in sign. One of the summons may be positive, but at the same time, there is another summand that is negative. When added together, they compensate for each other, leaving a final result. For a long time, scientists have not been able to unify the theory of relativity in quantum physics. Supersymmetry, however, allows infinities to be neutralized, making this unification easier. Einstein once compared his theory of gravity to marble. It is just as smooth, elegant, polished. Matter, on the other hand, resembles wood, jagged, chaotic, and lacking proper geometric structure. Einstein's ultimate goal was to create a unified theory that combined marble and wood. That is, a theory made entirely of marble. That was Einstein's dream. String theory, in this case, combines marble, bosons, and wood fermions. Steven Weinberg, Nobel Prize winner, wrote, "Although symmetries are hidden from us, we can feel that they are implicitly present in nature, governing everything around us. This is the most fascinating idea I know. Nature is much simpler than it looks. Nothing gives me more hope that our generation really holds the key to the universe, that while we are still alive, we will be able to say why everything visible in this vast universe of galaxies and particles is logically inevitable." If we summarize all of the above in this video, it turns out that symmetry is very much like the key to unifying all the laws of the universe. Symmetry brings order to chaos by forming an ordered system of chemical elements and particles, helps to identify missing links in theories by predicting new elements or particles, finds connections between objects that seem independent, leads to the discovery of new phenomena, such as antimatter, spin, and quarks, eliminates unwanted consequences that can destroy a theory, modifies the original classical theory. It is believed that at the beginning of the birth of the universe, there was one single super interaction whose symmetry included all particles. However, this symmetry began to break down. First, gravity stood out, then nuclear interactions, leaving the electromagnetic forces by themselves. Thus, the current world appears fragmented, where each interaction is different from the other. The challenge for physicists is to reunite these broken pieces. Superstring theory has the potential to do just that. But there was a problem. It couldn't be expressed through one single equation. In 1995, an important event occurred that led to the emergence of M-theory. The crux of the problem was that there were 5 varieties of string theory, differing only in the way spins were organized. This raised questions, as most scientists believe that the universe must be unique. Physicist Edward Witten discovered that there is a hidden 11-dimensional theory called M-theory. Witten argued that the 5 different string theories can be interpreted as 5 ways of converting an 11-dimensional membrane into a 10-dimensional string. In other words, all these variants of string theory are different mathematical models of the same M-theory. It follows that string theory and M-theory are different projections of the same idea. But how can one 11-dimensional concept give rise to 5 10-dimensional ones? Imagine a beach ball. If you let almost all the air out, it will take the shape of a whiner. If you deflate it completely, you get a string. In essence, a string is a disguised membrane from which the air has been let out. Starting with an 11-dimensional ball, you can prove mathematically that there are 5 ways to deflate it, turning it into a 10-dimensional string. Just 2 years after the introduction of M-theory in 1995, Maldacena presented a truly phenomenal discovery. His research showed that supersymmetric Yang-Mills theory, which works in 4 dimensions, is mathematically equivalent to 10-dimensional string theory. This caused quite a stir in the physics world, and by 2015, the discovery had been cited in 10,000 papers, making Maldacena's work the most influential in high-energy physics. At the beginning of the video, we discussed the duality in Maxwell's equations between electric and magnetic fields. These equations retain their form if you swap these fields. Similarly, there are 5 10-dimensional string theories that are dual to each other because they all combine into a single 11-dimensional M-theory. That is, the duality suggests that the 2 theories are different sides of the same phenomenon. Nevertheless, Maldacena proved that there is an additional duality between 10-dimensional strings and 4-dimensional Yang-Mills theory. This finding was a surprise, indicating deep connections between gravitational and nuclear interactions in different spatial dimensions. Michio Kaku writes, "Typically, dualities are found between strings of the same dimensionality by rearranging the summons describing these strings. For example, we can often replace one string theory with another. This creates a whole web of dualities between different string theories that are defined in the same dimension. But duality between 2 objects defined in different dimensions was an event unheard of. The issue raised by this duality is not just a matter of academic reflection. It affects our understanding of nuclear interaction. For example, we already know that the best way to describe it is a gauge theory in 4 dimensions based on the Yang-Mills field. However, no one has yet been able to identify an exact solution to this theory, given that gauge theory can be related to 10-dimensional string theory. This points to a possible interrelated understanding of quantum gravity and nuclear interaction. This idea drew attention to the fact that key features of the nuclear interaction, such as the mass of the proton, could be best explained through string theory. This caused a real identity crisis among physicists. Nuclear physicists, who had traditionally studied conventional three-dimensional objects, were suddenly faced with the need to study string theory in 10 dimensions. This raised questions about the relationship between gravity and gauge theory. In addition, an interesting principle called the holographic principle was discovered. A hologram is a two-dimensional image that can reproduce a three-dimensional image using a laser beam. This is roughly how R2-D2 from Star Wars projected the image of Princess Leia. Haunted houses at Disneyland are also being created. There are three-dimensional ghosts gliding around you. Similarly, in black holes, all the information about the objects inside can be encoded on the two-dimensional surface of the event horizon. If you throw a Bible into a black hole, according to quantum mechanics, the information contained in the book cannot disappear. So where does it go? It probably gets distributed on the surface of the event horizon. So the two-dimensional surface of a black hole contains complete information about all the three-dimensional objects that have gotten inside. This discovery challenges our understanding of reality. We think of ourselves as three-dimensional beings, but perhaps we are actually part of a hologram. Maybe the three-dimensional world we perceive is just a shadow of the real one, which is actually 10 or 11 dimensions. Moving in 3 spatial dimensions, we thus perceive the movement of our real self in 10 or 11 dimensions. When we walk down the street, our shadow follows us and moves like us, except that it exists in 2 dimensions. Similarly, we ourselves may imagine shadows moving in 3 dimensions, but our real selves are moving in 10 or 11 dimensions. It turns out, string theory today continues to offer increasingly surprising conclusions. This indicates that we do not yet have a good understanding of the foundations on which it is based. For this reason, experimental verification of string theory seems premature. Once we uncover its real principles, we may be able to find a way to experimentally test it. Then, we will be able to say for sure whether string theory is a theory of everything or a theory of nothing. Thanks for watching. Subscribe to the channel so you don't miss the release of new videos.